You guys might have seen many stars in your life. We know the distance between some of them too. Of roughly 100,000 visible in the sky, only a few hundreds of them are labeled. But we know the distance between almost all of them. Have you wondered how? Let us take a look at some of the methods used in doing so. Place your thumb like this and close one of your eyes. When you close your right eye, your thumb will be moved in the left direction. This is known as the parallax effect. Similarly, we can find distances between stars using this method. For example, take Proxima Centauri. Observe it in December month. Find its relative position. Then, observe it in June. If we join Proxima and Sun, we get a right-angled triangle. Let's solve this using trigonometry. Tan theta equals the adjacent side by the opposite side. Thus, we know the adjacent side length. That is the distance between us and Sun. It's 1 AU, astronomical unit. Taking distance between us and Proxima BD, we have tan theta equals 1 by d. Therefore d equals 1 by tan theta. For the sake of convenience, let's take tan theta equals theta, since theta value will be too small to calculate. Thus d equals 1 by theta. We will get the distance in a unit called parsec. Note, 1 parsec equals 3.262 light years. After all your calculation, we will get the answer d equals 1.3 parsec. So, the actual distance will be equal to 1.3 times 3.262 equals 4.24. Use your calculator or Google it. I am not a liar like others. Unfortunately, this understandable susceptible method is not applicable to all situations. We can only see up to 32,000 light years. But the universe is considerably big. Here we use the Hertz-Sprung-Russell diagram. For this diagram, we need luminosity, amount of light produced by the star, and color. After marking them on the graph, astronomers use a formula, the inverse square law. The formula is B equals L by 4 pi d squared. Don't get afraid. Let me explain. Here B is the brightness of a star observed from Earth telescope's apparent brightness. L is the actual brightness of the star. 4 pi d squared is nothing but the volume of stars, as stars are the sphere in shape. So how do we get the color? Our telescopes use a lot of filters and measure the wavelength of the lights produced by the star. Color or light. It's just the frequency of star. So it's represented by lambda. This lambda helps us to find the temperature of the star. But how? Using Wien's displacement law. That is T equals 0.0029 Kelvin meters by lambda. Here we get the temperature in the form of 0.0029 Kelvin meters divided by the temperature or wavelength we got from filters. We got our answers in Kelvin. Now let's start drawing Hertz-Sprung-Russell diagram. Up we have temperature, down the color, side luminosity. I may collapse you guys. Let me try to clear you in another video. In this diagram, every dot is a star. Do you find it difficult? Of course, astronomers find it difficult too. That's why instead of a single star, astronomers take a group of stars for convenience. This group of the star is called a globular star cluster. They take the group of stars and compare its luminosity, then arrange it in a graph. Then, they compare this graph with the HR diagram. The point where they match will give actual luminosity. Using this method yet, we can measure up to barely 160,000 light-years. That's why we use a certain type of star. Here comes the most interesting part of astronomy. Cepheid stars. These stars glow brighter and become dimmer in days or weeks. This time interval is called a period. They will glow unique like in the picture. When you want to measure the distance between a galaxy, check it's the Cepheid star, calculate period by observation. Then solve using inverse square law. Like this, you can measure up to 55 million light-years. What about further distances? We get them using supernova. A supernova occurs when a star runs out of energy to produce light. There are 3 types of them. We are getting benefited from a type 1a, for which brightening and dimming are very regular. Look at this picture. galaxy NGC 2403, before and after the supernova. Hope you can see the supernova there. Both of them are type 1a. If the distance to a faraway galaxy is required, one must first locate a type Ia supernova in it, which does occur regularly, and then measure its observed brightness. Comparing this result with the known maximum brightness achieved by all such supernovae, one can determine its distance using any of the methods. Since supernovae are extremely bright, this method is useful to very large distances, up to 10.2 billion light-years. Here we face our trouble, the gravitational redshift. But what is the redshift? Imagine your friend standing at the edge of a bridge. He sends you a message, and as the speed of message is slow, you will cross the bridge before the message reaches him. Similarly, as an object moves away from us, the sound or light waves emitted by the object is stretched out, which makes them have a lower pitch and moves them towards the red end of the electromagnetic spectrum, where light has a longer wavelength. The most accurate way to measure redshift is by using spectroscopy. When a beam of white light strikes a triangular prism, it is separated into its various components. But when you send the light through a hydrogen atom and then through a prism, the spectrum will not be the same. The hydrogen atom absorbs some fewer wavelength lights. This is known as the absorption spectrum. It varies for every single element. For example, let's take a galaxy and observe it using spectrometer, write down its absorption spectrum, then measure it with our absorption spectrum we made using hydrogen. They have a slight difference, right? This is the cosmological redshift. This is measured by a formula. Wavelength observed minus wavelength of the sample divided by the wavelength of the sample. By this, we can calculate redshift. For example, let it be 0.00000715. This redshift is directly proportional to the distance divided by the speed of light. To remove proportionality we use Hubble constant. And yeah, we know redshift, we know Hubble constant, we know the speed, we can now calculate distance, that is 46,200 times d divided by speed of light equals to 0.00000715. We get an answer to be 4.6 times 10 power 6. Converting this to distance, we get the answer as 1 million light-years. If you don't believe me, pause the video and Google it. This is the farthest point we have ever absorbed in space. Take a look at this. This is the farthest point we have ever absorbed in space. The GNZ 11 galaxy. This galaxy is about 32 billion light-years away. If we see this galaxy means we see the light from the star 32 billion years ago. So, we are seeing the galaxy which existed before the Big Bang. That's a kind of absurd. So, how do we observe this galaxy? By cosmological redshift. The light produced by this galaxy 400 years after the Big Bang, stretched and just reached us, comparing the absorption spectrum of stretched light and sample absorption spectrum. We can calculate redshift, then the distance. Hope you guys enjoyed the video. Subscribe to get stunning space facts and research article review. Tell me which video you want next.